So in this video, we're going to take some time to talk about what's probably one of the most frequently used strategies when evaluating a limit analytically, which simply means using algebra, not doing epsilon delta proofs, not using L'Hopital's rule. So this would be very early in your calculus course. You'd likely be working on problems like these. And that method is going to be to factor and cancel. And I've got 5 examples. We're going to try to discuss all of these. They definitely are going to ramp up in difficulty as we make our way through them. But we'll go ahead and get right into it. So this first example is definitely the most straightforward. I'm going to take my first step being the same every single time, and that's I'm going to try to figure out what happens if I put 1 in place of all these x's. So you're going to want to look for a signal when you're evaluating a limit, and you get that signal by placing what x is approaching in place of the x's. And if you do that here, what you end up with is you end up with 0 divided by 0. Now I did not say that this limit is equal to 0 over 0. 0 over 0 is an indeterminate form. It doesn't have a fixed value. So I'm listing the signal in the upper corner of the page. This is signaling to me that I need to do some algebra and get something to cancel. So the mistake that I would tend to see students make a decent amount early on in a calculus course is saying, hey, I've got to cancel stuff. I've got an x squared here. I've got an x squared here. I'm able to cancel those. Well, what's really around the top and bottom of this fraction is a set of parentheses. And if I'm reaching into the parentheses to do the division before I do the operations within the subtraction, within the parentheses, the addition and subtraction, I'm violating the order of operations. So what I'm going to have to do is I'm going to have to get the top and bottom of this expression factored. So we're factoring trinomials here, so we're going to unfoil. I would need first times first for the numerator to give me the first piece of the numerator. I would need last times last to give me the last piece of the numerator, -2, and then I would need to pick these values appropriately so that the outer and the inner multiplications of FOIL give me what I have in the middle, which in this case is plus 1x. So for the numerator, x plus 2 and x minus 1 makes that happen. I have to take a similar strategy with the denominator. It's also 3 terms. So first times first is going to have to give me the first piece. Last times last is going to have to give me the last piece. But then the outer and the inner multiplications from FOIL are going to have to give me minus 3x. So minus 2 and minus 1 would be the combination that I want for last times last. Once you have this factored, you are not reaching into parentheses to do the cancellation of these common factors. So you're able to cancel the x minus 1 and the x minus 1. Now that you've had some cancellation occur, it's appropriate to try to reevaluate the limit. Put 1 here, put 1 here, you get 3 in the top, -1 in the bottom. This limit has a value of -3. Example 2. Same initial step. Now I do have a different variable here. It's h approaching 0. You'll see this quite a bit early in your calculus course because you're ramping up to eventually define a derivative. But for now, we just have to realize h is serving the role that x normally serves within these limits. So h is approaching 0. I'm going to put 0 in place of this h. I'm going to put 0 in place of this h. I get the same signal, 0 over 0. Again, that's an indeterminate form. It's not going to give us the result. It signals for us, do some algebra, get something to cancel. After some stuff cancels, then try to reevaluate the limit. Now the algebra here is actually a little bit lengthier than what we did in the last problem. Before I can factor and cancel, I'm going to have to expand this numerator. In other words, get rid of those parentheses. And I cannot distribute that exponent. I'm going to have to write that numerator as repeated multiplication, 1 plus h times itself, 3 times total. Just have that -1 hanging out at the end of the numerator, and then this h is also just along for the ride within the denominator. So when I expand 1 plus h times 1 plus h, foiling that out, gives us this result, 1 plus 2h plus h squared. Still have to multiply by this third factor of 1 plus h. And again, the -1, end of the numerator, h in the denominator, still just along for the ride. When I expand this, I just need to make sure I do 6 multiplications. The 1 has to get multiplied by both of these, the 2h has to get multiplied by both of these, and the h squared has to get multiplied by the 1 and the positive h. If you do those 1, 2, 3, 4, 5, 6 multiplications, you get what you see across the first 6 items in this numerator. After that has been fully expanded, you finally have the opportunity to do some cancellation. The 1 that you get when you do first times first is able to cancel with that -1 that's just been hanging out at the end of the numerator across all these lines. I have h and 2h that combine to 3h, 2h squared and h squared that combine to 3h squared, and then this h cubed doesn't have anything to combine with, so it just copies into the next line. At this point, you can try to reevaluate the limit, but putting 0 in place of all of these h's is going to give you 0 over 0 once again. So how can I get past 0 over 0 now? Well, I can factor a common factor of h from each of the items in the numerator. So when I do that, h is undistributed from each of the 3 items in the numerator. After this h is outside that set of parentheses, I'm not reaching into parentheses to cancel the h that I've removed as a common factor with the h that's in the denominator. After that cancellation occurs, now put 0 in place of the only 2 remaining h's, and you end up with an answer of 3. This one's actually maybe the quickest that we've discussed, but I definitely see students tend to be scared off when they see things like e in their problems, e to a power within their problem. Take the same approach, same strategy. I'm putting 0 in place of these x's. I'm putting 0 in place of these x's. I get 0 times something in the numerator, so I definitely get 0 in the numerator, and then I get 0 plus 0 in the denominator. So once again, I get that signal, 0 divided by 0. What does it tell us to do? Do some algebra, get something to cancel between the top and bottom. After that happens, try to reevaluate that limit. The top is actually already factored. It's written as multiplication, right? The process of factoring is simply the process of rewriting an expression as multiplication. That's already true about the numerator. It's already multiplication. So you notice I just copied my numerator into this next line, and I notice I could do a greatest common factor removal from the denominator. Both of those share a factor of x, so if I undistribute an x from both terms in the denominator, that's going to have an x outside this set of parentheses, and then I'm going to be left with an x from the x squared, and then a 1 when I undistribute x from x. I can then cancel. I'm not reaching into parentheses to cancel this x and this x, so I can cancel those x's. After that happens, reevaluate the limit. Try to put 0 back in place of the x's. So 0 goes in place of the x in that exponent, and the exponent becomes a positive 1. 0 goes in place of the only x that's left in the denominator, and your denominator is also a positive 1. E to the first divided by 1 is just e to the first, or e. Another problem here that involves e to a power. Again, don't be scared off by this. Take the same strategy. So the strategy here, again, is going to be put 0 in place of your x's, look for a signal. So in this case, the signal is, once again, 0 divided by 0. What's it mean? Do some algebra, get something to cancel. Once something cancels, try to reevaluate the limit. The factoring here is definitely the sneakiest that we would have done so far within this discussion. You have multiplication within this exponent right here, 2 times x. You multiply exponents when you raise one power to another power, and I think in this case it's more convenient for us to rewrite the numerator like you see here, because now it's something squared, this is 1 squared, minus something else squared, e to the x squared. This numerator is now a difference of squares. If I factor the numerator as a difference of squares by rewriting it as a pair of conjugates, 1 minus e to the x in this case, and again it's the first thing that's being squared minus the second thing that's being squared, and then times the first thing that's being squared plus the second thing that's being squared. The order of the plus and the minus don't really matter here because they're ultimately sets of parentheses being multiplied together, and multiplication is commutative. But if you get that numerator factored, what you'll notice is you can stick a set of parentheses around the denominator, and you can cancel that factor of 1 minus e to the x from the numerator with the entire denominator. After that happens, 0 goes in place of the only x that's left. You get 1 plus e to the 0. Anything to the 0 power other than 0 is 1. 1 plus 1 is 2. Last example is definitely the trickiest in this discussion. Here, again, same initial strategy. Put 0 in place of all of these x's. You do get 0 over 0. That doesn't always happen when you evaluate limits, but I want to make sure that you do that as your first step. Sometimes you get a different signal. We'll talk about some of those other signals in some upcoming videos. So what can I do? Well, I can factor the numerator, right? If I'm going with the factor and cancel strategy, which doesn't always work, but it works a decent amount of the time, I can remove a GCF, Both of these share an x within the numerator, and the denominator is a little trickier. I have maybe seen students have the tendency to want to like do the square root of x to the fourth, do the square root of 2x squared, and add the results. There's not a property of roots that allows us to do that. But I can factor out a greatest common factor of x squared from both pieces in the denominator. So when I get the denominator, the portion of the denominator that's under the root written as multiplication, I have something that I can now do the square root of times something else that I am not going to really have as easy of a time doing the square root of. Now here's the trickiest thing about this particular limit. When I take the square root of x squared, I do have to consider the fact that I don't know now whether or not x is positive or negative. I am going to have to realize that I can square a positive or I can square a negative to get this positive x squared that's sitting right there. So I do have to consider both a plus and minus answer for the square root of x squared. So the square root and the square are going to cancel, which is why you see an x to the first here. But I do have to take into account the fact that x may be positive, x may be negative. So this is what the limit turns into. Now here's the trickiest aspect of this problem. Obviously the algebra was the sneakiest that we've seen in any of these examples, but now I'm approaching zero. I know if I'm approaching zero on the bigger side, my x would be positive. And if I know I'm just isolating the bigger side, I know I can just take the positive sign in front of the x in that denominator. And if I do that, because this is multiplication here, this is multiplication here, I can cancel these x's. And when I put 0 in place of the x's that remain after that cancellation occurs, I get 1 over the square root of 2. Now what if I consider the smaller side of 0? On the smaller side of 0, I know that x is negative. If I know x is negative, the square root of x squared is negative x, which is why you see on this limit on the smaller side, I've just included the negative. I can still do this cancellation, but what ends up happening is I now have a negative in front of that square root in the denominator. So on the smaller side of 0, when I put 0 in place of these x's that remain, I do end up with 1 over the square root of 2, but it now has the opposite sign. So this is a situation where our one-sided limits do not equal each other, and when that happens, the general limit is going to be one that does not exist.